Alrighty, we're going to look at a pattern of inheritance called sex-linked inheritance, which gets a little complex, but it's important for us to understand why it does. And the way we are going to start there is with looking at all 23 pairs of chromosomes. And so if we look right here, this is my version of all the 23 pairs of chromosomes that humans have. And maybe you might not recognize them because sometimes they look like X's, and the only reason they look like X's is because they've been duplicated during the synthesis phase before meiosis. So all I'm showing is all 23 pairs of chromosomes, but in interphase or before they've been multiplied. So it's still the same number of chromosomes, they just haven't been duplicated. So what's important when we look at this is that we've got 22 pairs of chromosomes here that are called autosomal chromosomes. And autosomal chromosomes are 1 through 22 that are not involved in the determination of gender. However, these 23 paired right here, the 23rd pair, are called sex chromosomes or X-linked chromosomes, the 23rd pair, and these are involved in gender determination. And so in order for, I guess my question here is, let's see. Let me get a pen. So if you're a male, you have an X and a Y. You have an X and a Y, so I'll put that up here. X and a Y. And if you're a female, you would have two X chromosomes. And so if remember, how many genes do we have for a trait? We have 2. And how many do we pass? We only pass 1. So if we put a Punnett square here of what the possible combinations of X and Y's can be, when a male and female reproduce, what are the chances of having a female? What are the chances of having a male? And of course, it's 50-50. There's 50% chance of a male-female having a girl, and 50% chance of having a male. And that's really not probably all that new to you. But what is important here is the difference between the autosomal chromosomes and the chromosomes on the X and Y chromosomes. And so what we want to look at is the alleles on all the other chromosomes in your body. You have about 1,000 per chromosome, about 1,000 genes per chromosome. And on the X chromosome, you have about 1,000 genes per chromosome. However, what I want you to notice is the Y chromosome is much, much smaller than the X chromosome. And the fact is, it's so small that there's really only about 30 different genes on that chromosome. There's not many at all. And most of them are basically called SRY genes that produce testosterone and give males their male reproductive organs. That's really the job of the Y chromosome. And so what that means is if you put them side by side, there's going to be many things on the X chromosome, or many genes on the X chromosome, that aren't on the Y chromosome. And my question is, so can males be heterozygous for traits located on the X chromosome? And the answer is no, because they only have one X chromosome. They only have one gene for that trait. So males cannot be heterozygous for traits located on the X chromosome, and they cannot be heterozygous for sex-linked traits. How many alleles do males have for sex-linked traits? The answer is 1. And so in males, what happens to an allele, dominant or recessive, if it's located on the X chromosome? The answer is it's always expressed whether it's recessive or whether it's dominant. And a common sex-linked trait that maybe you've heard of is colorblindness. And the reason why males tend to be colorblind, or the probability of being male and colorblind is higher than females, is because it's a sex-linked trait. And if we look here, the X chromosome is much, much bigger than the Y, and the allele that codes for colorblindness is maybe right in the middle of the X chromosome. And if an individual, a male, has a big C on their X chromosome, then they'll have normal vision. But if an individual has a little c on their X chromosome, since they only have one gene for a trait when it comes to sex-linked traits, they don't have anything else to cover it up. They don't have another uh, big C or dominant trait on their Y chromosome um, to be dominant over the recessive little c. So for males, it's more common because there's really they only have one gene for a trait. So let's take a look at an example. And we will always tell you if it's sex-linked or incomplete or multiple alleles. It'll always tell you that in the problem or maybe in the heading. But a sex-linked recessive little h produces hemophilia in humans. A woman who is heterozygous for the condition marries a man who does not have hemophilia. What are the expected phenotypic and genotypic ratios for male and female children? So again, what we're going to do is write down all the information that we know. And what we know is big H, little h. So big H means no hemophilia. And hemophilia is a blood clotting disorder. So what happens if someone has hemophilia and they get cut, they have a much difficult time stopping the bleeding, and they can bleed out, and even a little bruise can be really, really dangerous. And right now we've got a woman who is heterozygous for the condition who marries a man who does not have hemophilia. So the notation we're going to have here is we have to pay attention now to women and to the men. Before we didn't have to really pay attention to that too much. So the way we're going to do this, if it's a male and a female, we're going to write females X, X, males X, Y. And on the female, she is heterozygous for the condition. So we'll give her a big H and a little h. And the man does not have hemophilia. And so that means he's got a big H. And since there's no gene on the Y because it's so small, we're not going to put anything there. So he only has one gene per trait, which is an exception to our law of segregation, have two, pass one. In this instance, he's going to have one and pass one. And so when we go to make our Punnett square, like so, we'll put the female on top, and we'll put male on the left side. And so if we do our Punnett square, that's supposed to be an H. And then we got, here we go. So it asks, what are the genotypic and phenotypic ratios of males and females? So what we have to do now is we have to say female. And I would say the genotypic ratio is 1 to 1. And it would be 1 to 1 XH, X big H, to X big H, and X little h. And the question is, well, do any of the females have hemophilia? And the answer is all do not have it. Because they all have at least one big H, one dominant allele. So now let's take a look at the guys. So males. And so the genotypic ratio, again, is a 1 to 1 ratio of big H by itself and Y, and then little h and Y. And so when we look at the phenotypic ratio, this individual has a big H, so that would not have hemophilia, but this one would. So really what we have is it's a 50% chance for a male will not have it. And a 50% chance that the male a male child will have hemophilia. And so again, these sex-linked traits are much more common in males than in females. So this would be my answer. Alrighty, I'm going to do one more problem here. If you feel really confident and good and you want to move on, that is totally fine. But if you want to stick around for the next problem, that is okay as well. So here's number 2. So a sex-linked recessive allele little b produces red-green color blindness in humans. A normal woman whose father was colorblind marries a colorblind man. So again, my strategy is really write down everything that I know. So we'll use a big B and little b here. Big B for, we'll say, for normal. And then little b for color blindness, since it's a recessive trait. And let's look at our parents here. We've got, again, we have to figure out, we've got mom, and then X and Y is dad. And so we have a normal woman whose father was colorblind marries a colorblind man. So let's start with the guy. He's colorblind, so he's a little b. If a normal woman means she has at least one big B, but if her father was colorblind, remember, he's guaranteed, if it's a girl, he's going to pass his X. And if he was colorblind, his X is always going to have a little b. So we know now that the female must be heterozygous for color blindness, because the father is going to pass the X, and his only X is going to have the colorblind allele on it. If he passes Y, then the normal woman would actually be male. So the question here is, what is the probability her first child will be a colorblind boy? And so what we'll do here, just to answer all those questions, is we'll have to make our Punnett square. And it doesn't matter where you put them. And so let's see. All right, so there's our Punnett square. What is the probability that their first child will be a colorblind boy? So there's 1 out of 4 here. So the answer to A would be 25%. And then of the girls produced by these parents, what percentage of the girls is expected to be colorblind? So we're only going to look at these 2 here. And so it looks like this individual would be normal, but this individual would be colorblind. So that's a 50%. So 50% of the girls. And then finally, of all the children, what proportion of them is expected to be normal or have normal for color blindness? And so these 2 individuals would be colorblind, these 2 would not. So again, our answer is 2 out of the 4, so 50%. Hope this helps. Thanks for watching.